Dear learner, welcome to this lecture of Unit 18 titled Use of Protective Devices and Safety Regulations of Module 6 on Wires and Accessories of the MOOCs course on Electricity and Electrical Wiring. This module has 3 units. In Unit 16, we discussed electrical wires and cables, and in Unit 17, we discussed electrical joints and accessories. In this module, we will discuss the protective devices and safety regulations as mentioned. Introduction. This session is on the use of protective devices and safety regulations. This lecture explores the role of protective devices in electrical systems, their types, working principles, applications, and guidelines for safely handling tools and equipment. Ensuring safety and stability in electrical operations is critical for both personnel and system integrity. The learning outcomes. By the end of this lecture, learners will be able to understand the types and functions of protective devices. They will be able to identify key protective devices such as starters, relays, and circuit breakers and explain their working principles, power ratings, and applications in electrical systems. They will also be able to apply safe practices in electrical work. Basically, to demonstrate knowledge of safe handling procedures for tools and equipment, including the use of personal protective equipment PPE and compliance with lockout, tagout, LOTO protocols. And they will also be able to recognize and adhere to safety regulations. They will be able to interpret relevant international and national standards for electrical safety, including guidelines for grounding, device rating, and emergency protocols. Protective devices in electrical systems. Protective devices are essential components of electrical systems designed to safeguard both equipment and personnel. Their primary function is to detect faults such as overloads, short circuits, and leakage currents, and to isolate the affected sections of the system. This ensures that the electrical network remains stable, preventing further damage and minimizing risks to individuals working in or near the system. Faults in electrical systems can lead to equipment damage, operational downtime, and even serious safety hazards like fires or electric shocks. Protective devices such as circuit breakers, relays, and residual current devices act as the first line of defense. By promptly interrupting current flow during abnormal conditions, these devices prevent the escalation of faults and ensure that the unaffected portions of the system remain operational. For example, circuit breakers use thermal or magnetic triggers to detect and isolate excessive currents, while relays monitor and control circuits to prevent overloads or overheating. Residual current devices further enhance safety by detecting leakage currents, which could otherwise pose a shock risk to personnel. In addition to their technical role, protective devices contribute to regulatory compliance and operational efficiency. By maintaining system integrity and reducing hazards, they minimize costly repairs and enhance workplace safety. Ultimately, these devices are indispensable for ensuring the reliability and safety of electrical systems in both domestic and industrial settings. Starters in electrical systems. In this section, we will explore starters, which are vital devices in electrical systems. Starters are designed to control the starting and stopping of electric motors while providing essential protection against overload. They are critical in ensuring the safe operation of motors by managing the initial surge of current and preventing damage to the motor and connected equipment. A starter is a device specifically designed to regulate the starting and stopping of electric motors. Beyond simply switching the motor on and off, starters also protect against conditions such as overloading or electrical faults, which could lead to equipment failure or downtime. By limiting the starting current and offering overload protection, starters enhance both motor efficiency and longevity. Types of starters. Now let us look at the three main types of starters commonly used in electrical systems. Each type is designed for specific motor requirements depending on factors such as torque and capacity. Direct online starter. The direct online starter or DOL starter is the simplest and most commonly used type. It connects the motor directly to the power supply and is best suited for motors with low starting torque requirements. Advantages: the DOL starter is easy to install, cost effective and reliable for small motors. Limitation: it draws a high inrush current, making it unsuitable for larger motors as it can cause mechanical stress or voltage dips in the electrical system. Star Delta starter. A star delta starter is designed for high capacity motors. It reduces the starting current by initially connecting the motor in a star configuration and later switching to a delta configuration for full operation. Advantages: this method lowers the initial current demand, making it suitable for industrial applications requiring smooth motor startups. Limitation: while effective for larger motors, it is slightly more complex to install compared to DOL starters. Soft starter. Soft starters gradually increase the voltage supplied to the motor during startup, minimizing mechanical stress and electrical surges. This technology is particularly useful for applications requiring precise control of motor acceleration. Advantages: it provides a smoother start, reducing wear and tear on equipment and prevents sudden current spikes. Limitation: soft starters are typically more expensive than DOL or star delta starters. Power ratings. The power ratings of starters vary based on the motor they are designed to control. For smaller motors, starters typically handle capacities of a few kilowatts. However, for industrial applications, they can accommodate motors with capacities ranging into hundreds of kilowatts. Selecting the appropriate starter with the correct power rating is crucial to ensure reliable motor operation and protection. Working principle. Starters operate by limiting the initial current during motor startup. This is achieved by either reducing the voltage supplied to the motor or introducing resistance into the circuit. Most starters also integrate overload protection, which is often provided through thermal relays that detect abnormal current conditions and shut off the motor to prevent damage. Applications. Starters are used across a wide range of applications to control and protect electric motors. Most common examples include industrial machinery, starters ensure the safe operation of motors used in heavy equipment, pumps and compressors. They regulate motor performance to meet varying load requirements. Conveyor systems. Starters help maintain consistent motor operation to avoid sudden surges that could disrupt production. By providing overload protection and managing starting currents, starters contribute significantly to the efficiency and safety of these systems. To summarize, starters are critical devices for the safe and efficient operation of electric motors. Whether using a DOL starter for smaller motors or star delta starter for high capacity motors or a soft starter for precise control, the appropriate choice depends on the specific application requirements. With their ability to limit starting currents and protect against overload, starters play a key role in prolonging motor life and ensuring reliable performance across industries. Relays in electrical systems. Relays are vital components in electrical systems, acting as electromagnetic switches that open or close circuits in response to electrical signals. Their primary function is to control the flow of electricity between circuits, enabling automation and protection in a wide variety of applications. In this section, we will cover the definition of relays, their types, power ratings, working principles, and common applications. A relay is an electromagnetic switch that operates by responding to an electrical signal. It allows one circuit to control another, often isolating high power systems from low power control circuits. This isolation ensures safety and efficient operation in both industrial and domestic settings. Types of relays. Relays come in several types, each designed for specific functions and applications. Let's explore the three primary categories. Number 1, electromechanical relays. Electromechanical relays or EMRs operate using a coil and mechanical contacts. When current flows through the coil, it generates a magnetic field which physically moves the contacts to either open or close the circuit. Advantages: these relays are reliable, cost-effective, and capable of handling a wide range of currents and voltages. Limitations: since they rely on mechanical movement, they may have slower response times and are subject to wear and tear over time. Number 2, solid-state relays. Solid-state relays use semiconductor devices such as thyristors or transistors to perform switching operations. They have no moving parts, which makes them faster and more durable than EMRs. Advantages: faster switching speed, silent operation, and resistance to mechanical wear. Limitations: typically more expensive than electromechanical relays and may generate heat during operation. Number 3, thermal relays. Thermal relays are designed to provide protection against overheating. They use a temperature-sensitive element such as a bimetallic strip to detect excessive heat caused by overcurrent. When a preset temperature threshold is reached, the relay trips to prevent damage. Advantages: simple and effective for motor overload protection. Limitations: they are limited to applications where temperature monitoring is critical. Power ratings. Relays are versatile devices capable of handling a wide range of power ratings. They are commonly used for low power control circuits, with typical ratings of 1 to 5 amperes. However, industrial systems often require relays that can manage currents of several hundred amperes. Selecting the appropriate power rating is essential to ensure the relay can handle the load safely and effectively. Working principle: relays operate by utilizing an electromagnet to trigger a switching mechanism. Here's how it works. When an electrical signal is applied to the relay's input, it energizes the coil, creating a magnetic field. This magnetic field either pulls or releases a movable armature, which in turn opens or closes the relay's contacts. Depending on the type of relay, this switching can be mechanical, as in EMRs, or electronic, as in solid-state relays. By isolating control circuits from load circuits, relays enhance safety and allow for efficient automation of electrical systems. Applications: relays are indispensable across a wide range of electrical and industrial applications. Some common uses include motor protection. Relays monitor conditions such as overcurrent or overheating and disconnect motors to prevent damage. Circuit automation. Relays are used to automate switching operations in processes like lighting control, conveyor systems, and assembly lines. Industrial and domestic switching systems. Relays enable the control of high power devices such as HVAC systems from low power control circuits. These versatile applications highlight the importance of relays in maintaining efficiency, safety, and reliability in modern electrical systems. To summarize, relays are crucial components in electrical systems, offering control, protection, and automation. With types such as electromechanical relays, solid-state relays, and thermal relays, they cater to diverse operational needs. By understanding their power ratings, working principles, and applications, you can ensure their effective use in both industrial and domestic contexts. Relays are, without doubt, an indispensable part of any reliable and safe electrical setup. Circuit breakers in electrical systems. Circuit breakers are essential components in electrical systems designed to interrupt the flow of current during fault conditions such as overloads or short circuits. By doing so, they prevent damage to electrical equipment, minimize hazards, and ensure system stability. In this session, we will discuss the definition of circuit breakers, their types, power ratings, working principles, and key applications. A circuit breaker is a switching device that automatically interrupts current flow when a fault occurs in the electrical system. This prevents excessive current from damaging equipment, wiring, or causing dangerous conditions like fires. Circuit breakers are designed to act quickly, restoring safety and allowing for the efficient management of electrical systems. Types of circuit breakers. Circuit breakers come in various types, each designed to address specific fault conditions and application requirements. Let's explore the most common types. Miniature circuit breakers or MCBs. Miniature circuit breakers or MCBs are compact devices used in domestic wiring to handle low currents, typically up to 100 amperes. Advantages: MCBs are cost-effective, reliable, and suitable for residential or small-scale applications. Applications: they are commonly used to protect lighting circuits, power outlets, and household appliances. Molded case circuit breakers or MCCBs. Molded case circuit breakers or MCCBs are designed for higher current ratings ranging from 100 ampere to about 2500 ampere. They are typically used in commercial and industrial settings. Advantages: MCCBs provide adjustable trip settings, making them versatile for different load conditions. Applications: they are used in distribution boards, large motors, and industrial equipment. Residual current circuit breakers or RCCBs. RCCBs, also known as residual current devices or RCDs, are designed to detect and isolate leakage currents, protecting against electrical shocks. They trip when there is an imbalance in current, which often indicates leakage through an unintended path, such as a person. Applications: RCCBs are essential for ensuring safety in bathrooms, kitchens, and other areas where electrical equipment may come into contact with water. Air and vacuum circuit breakers, ACBs or VCBs. Air and vacuum circuit breakers are heavy-duty devices used in industrial applications for very high current ratings. Air circuit breakers use compressed air to extinguish the arc during fault interruptions. Vacuum circuit breakers use a vacuum as the medium for arc extinction, offering high efficiency and low maintenance. Applications: commonly used in power plants, substations, and high voltage industrial systems. Power ratings: circuit breakers are rated based on current, voltage, and interrupting capacity. The ratings typically range from as low as 1 ampere for smaller devices such as domestic circuits to 100 kiloampere for high capacity industrial systems. Selecting the correct rating ensures the breaker can handle the maximum fault current without failing or causing additional damage. Working principle: the trip unit of a circuit breaker detects abnormal current or fault conditions and activates the operating mechanism to open the circuit. The type of trip unit determines the method of fault detection. In the most commonly used circuit breakers, a solenoid or electromagnetic coil generates a strong magnetic field during a high current surge. The field pulls the plunger, triggering the trip mechanism. Thus, it operates almost instantaneously for large fault currents. Applications: circuit breakers are versatile devices used in a variety of settings to ensure electrical safety and system stability. Electrical distribution boards, MCBs and MCCBs protect residential and commercial wiring from faults. Power plants, ACBs and VCBs are used to safeguard high voltage systems and ensure reliable power distribution. Industrial control systems, circuit breakers protect machinery, motors, and other equipment from damage due to overload or short circuits. These applications highlight the critical role of circuit breakers in ensuring safe and efficient operation across different environments. To summarize, circuit breakers are indispensable in electrical systems, providing protection by interrupting current flow during faults. With types such as MCBs, MCCBs, RCCBs, and high-capacity ACBs and VCBs, they address a wide range of needs from residential safety to industrial power management. By understanding their power ratings, working principles, and applications, you can make informed decisions about their use to ensure safety, reliability, and efficiency in electrical systems. Dear learner, after discussing the various protective equipment used in electrical systems, let us now test our understanding by attempting some multiple choice questions. Safety in electrical work. Electrical work poses significant risks if safety practices are not strictly followed. Proper handling of tools, adherence to safety regulations, and awareness of emergency protocols are essential to prevent accidents, equipment damage, or injuries. This session focuses on two key aspects: safe handling of tools and equipment, and safety regulations. By implementing these practices, you can ensure safer and more efficient electrical operations in any setting. Safe handling of tools and equipment. The general guidelines are: when working with electrical systems, follow these general safety practices, which is essential to minimize risks. Number 1, inspect tools for damage. Before starting any task, carefully inspect all tools for damage, such as frayed wires or worn out insulation. Damaged tools can lead to electrical faults or injuries. Replacing or repairing defective tools is critical for maintaining safety. Number 2, use insulated tools. Always use tools with insulated handles when working on or near live circuits. Insulated tools act as a protective barrier, preventing accidental contact with live components. Number 3, wear personal protective equipment, PPE. PPE such as insulated gloves, safety goggles, and non-conductive safety shoes provides an additional layer of protection against electrical hazards. Number 4, disconnect power sources before servicing. Before performing maintenance or repairs, ensure that the power source is completely disconnected. Verify that circuits are de-energized using a reliable testing device before proceeding with the task. Specific safety practices. In addition to general guidelines, the following safety practices can further enhance safety during electrical work. Avoid metal ladders. When working near live circuits, avoid using metal ladders as they conduct electricity and increase the risk of shocks. Instead, use fiberglass or wooden ladders, which are non-conductive. Verify voltage ratings of tools. Tools such as multimeters and testing devices must be rated for the voltage level of the circuit being tested. Using incorrectly rated tools can result in equipment damage or personal injury. Adhere to lockout, tagout, or LOTO procedures. LOTO is a critical safety protocol to prevent accidental energization of equipment during maintenance. It involves isolating energy sources and clearly labeling them to ensure they remain off until the work is complete. This practice is especially important when multiple personnel are working on the same equipment. Safety regulations. Electrical safety is guided by international and national standards that provide frameworks for safe design, installation, and operation. International standards. Organizations such as International Electrotechnical Commission (IEC) or Institute of Electrical and Electronics Engineers (IEEE) set globally recognized guidelines to ensure electrical safety and reliability. National standards. In addition to international standards, countries have their own regulations such as National Electrical Code of India, British standards in the United Kingdom, and National Electrical Code in the United States. Compliance with these standards ensures that electrical systems meet the required safety and performance benchmarks. Key safety practices. In addition to adhering to standards, implement these key practices to ensure safety and compliance. Use appropriately rated devices. Always select protective devices such as circuit breakers, relays, and starters that are rated for the circuit's power demands. Underrated devices may fail under fault conditions, posing significant risks. Ensure proper grounding. Proper grounding of electrical systems and equipment is critical for directing fault currents safely into the ground, preventing shocks and damage. Conduct regular testing and maintenance. Regularly test and maintain protective devices to verify their functionality. Fault devices may fail to operate during emergencies, leading to hazardous conditions. Emergency protocols. Electrical emergencies require quick and effective responses to mitigate risks. Consider the following protocols. Number 1, fire extinguishers for electrical fires. Maintain fire extinguishers rated for electrical fires in accessible locations. These extinguishers are specifically designed to handle fires involving live electrical equipment without posing additional risks. Number 2, first aid and emergency training. Train all personnel in basic first aid, including how to respond to electrical shocks or burns. Workers should also be familiar with emergency shutdown procedures and evacuation plans. Prompt and informed actions during emergencies can save lives and reduce damage. To summarize, ensuring safety in electrical work requires a combination of proper tool handling, adherence to safety regulations, and preparedness for emergencies. Protective devices like starters, relays, and circuit breakers are fundamental for maintaining safe and efficient operations. By conducting regular maintenance and understanding the functionality of these devices, risks can be minimized and compliance with the standards can be maintained. Dear learner, after discussing the safety practices to be adopted while dealing with electrical systems, let us now test our understanding by attempting some questions. Dear learner, with this we come to the end of this session. Thank you for your attention. Prioritizing safety and regulatory compliance in all aspects of electrical work is not just a best practice, it is a necessity for protecting both personnel and systems. Please refer to the additional resources for further study. Thank you.